today's lecture, we will be covering Chapter 2, where we will look at the concept of an atom. Throughout this chapter, we will take a deep dive through history and look at the different iterations and discoveries of the atom as we went through the ages. What is an atom? To begin with, let's just kind of take a moment to define what an atom is. Everything is made up of atoms, and atoms are the smallest unit of measurement for matter. Every single type of element has its smallest unit as an atom. So not all of the atoms are going to be the same. Each element is going to have its own type of atom. On Earth, there are about 90 elements which are naturally occurring as atoms. Each of these elements is going to have its own unique chemical and physical properties, from its size to the amount of electron density it has to how it reacts with other molecules. There are also about 20 synthetic elements which are created by scientists. The concept of an atom originated with Leucippus, who back in 500 BC originally looked at a pool of water and thought about the water being able to separate into drops which could then continuously be subdivided into smaller and smaller drops. He reasoned that ultimately there would be a tiny particle of water which could be no longer divided any further. It was this tiniest drop of water that he named as atomos, or an atom. Now, this isn't exactly correct, but it is the foundation for our modern definition of an atom. These original discoveries and theories were swept under the rug around 100 years later when the famous Greek philosopher Aristotle declared that the concept of matter was continuously and infinitely divisible rather than having a discrete set of divisions that could occur and a small particle like an atom existing. He classified matter into 4 different elements which would be divisible in a continuous fashion. The 4 elements as defined by Aristotle were fire, water, earth, and air. Aristotle's view was considered as an authority in many areas, and this view was readily accepted over the next 2,000 years, even though it was incorrect. Now we can fast forward to the early 1700s. It was at this point where a lot of the theoretical ideas behind the atom and matter and chemistry were beginning to have experimental evidence to back up the thoughts. The first set of experiments, and one of the original chemists in the early 1700s, was Lavoisier, and he was able to summarize his findings into the law of conservation of mass. This law states that during a chemical change, matter is neither created nor destroyed. As we go through many different chemical reactions in future chapters and this chapter, this law is extremely important to keep in mind. We're always going to need to start with the same amount of matter as we end with. Let's take a look at an example of the law of conservation of mass. On the left side of the arrow, we start as our reactant, our starting material, with 100 grams of mercuric oxide. This is a chemical compound that's composed of both mercury and oxygen atoms. If we're to take this compound and heat it to the point of combustion, then we have 2 products that we'll receive. It'll create the bond between the mercury and the oxygen and will break, and we will create 92.61 grams of mercury and 7.39 grams of oxygen. Now, it's important to note also that the weights of these 3 compounds will both add up to 100. We start with 100, and then after the reaction's complete, we end with 100 grams of oxygen and mercury. By the end of the 18th century, the chemists had deducted that compounds were made of multiple elements And at this point, they also figured out that a specific compound will always contain elements in a definite proportion or the same proportions. And this concept became the foundation for chemical formulas. A compound will always have the same ratio of the elements and will always have a constant set of properties that define that compound. Let's take a look at an example. The mineral seen in this left picture is called malachite. This is known as basic copper carbonate, and it has the formula with 2 coppers, 2 OH groups, and a CO3 group. Regardless of the source of this compound, whether it's from the natural mineral malachite or, for example, in letter C here, we have copper carbonate that's produced in the laboratory, it's always going to have the same chemical composition. It's always going to be composed of 57% copper, 5% carbon, 1% hydrogen, and 36% oxygen by mass. Another series of experiments that illustrated the law of definite proportions were conducted by Jöns Jacob Berzelius in Sweden in the early 1800s. In this set of experiments, he found that exactly 10 grams of lead reacted with exactly 1.55 grams of sulfur to create 11.55 grams of lead sulfide. Now, when an excess of sulfur was used, in this case 3 grams of sulfur, he found that only 1.55 grams of the sulfur would react with the lead. The other 1.45 grams of the sulfur were left as leftovers. When the amount of lead was increased, the same type of results occurred. We have 18 grams of lead, which reacts with 1.55 grams of sulfur. Now, since only 10 grams of lead can react with the 1.55 grams of sulfur, 8 grams of lead was left over. This is another example illustrating the law of definite proportions.